Hi, hi, Ojas and Akansha. Let's start in, I guess, 5, 6 minutes. So maybe a few other people can join the session. I guess we can start in 5, 6 minutes. Okay, so I guess no one else is joining the session. We can get started for now if someone else joins up. Yeah, we'll just see. So, hello everyone, just to reintroduce myself again, I'm Lakshya Saggi, the problem solving TA for the NPTEL Discrete Maths course for the Monday sessions. So, this will be our seventh session, I believe. And in this session, we'll be talking about graphs. So, we have moved on from like functions and induction and everything. And now we'll be talking more about algorithmic tools like graphs. So, this once again, I'll be assuming that you guys have gone through this week's lectures, like what are paths, what are cycles, basic definitions, and like the Havel-Hakimi theorem, which was discussed in this week, and we'll be discussing problems related to the same. So I guess we can get started now. I'll just share my screen and we can discuss the questions for today. Let me just share my screen, guys. I hope my screen is visible to everyone. If it is not, then if there are any issues with my screen or my voice, or if any doubt is not, if anything is not clear to you, like every time you can just ask me via chat and I'll try my best to help you. So yeah. So I guess we can get started for today. Okay, it works. So first again we'll be discussing some of the warm-up questions, and then in the later half we'll have like usual a bit of more difficult questions, a bit of more challenging questions which are not exactly a, which would not exactly be asked in your like exams or anything, but these will help you in your developing your concepts. So yeah. So first let's start with some basic warm-up questions. Uh, the first question is just asking us what is the degree sequence of the given graph. We are given a graph and we need to find out the degree sequence of it. And what does a degree sequence mean? I mean, this has been covered in the lectures, but uh, just what this means is we need to output the degree of, so degree sequence is nothing but degree, just a sequence of degrees of vertices. And in what sequence do we need to output these degrees with respect to the ordering defined, with respect to the labeling which has been defined. So A, B, C, D, E, F, G. So the first number in the sequence should be degree of A, second number should be degree of B, third number should be degree of C, and so on with respect to the ordering of vertices defined by their labeling. That is, just list out the degrees of vertices from A to G. There. So, would anyone like to point out the answer here? Okay, so Ojas and Akansha have already pointed out the answer, that the correct answer should be C. So let's just go through this for the viewers who are watching on YouTube also, so that they can be there also. So we need to find out the degrees of degree of A, degree of B, degree of C, and so on. So you can see that the vertex A has 4 outgoing edges. So the degree of A is 4. Similarly, B has 4 outgoing edges. Degree of B is 4. The options A and D are already ruled out. So it is 4 comma 4. Then C has, so maybe we can just write down the degree sequence also. So sequence is, I guess we can get started. So the vertex A had 4. So first vertex has 4. Then B again has a degree of 4. Then C only has 3 outgoing edges. Then D also only has 3 outgoing edges. Then E has 3 outgoing edges. Then F has 5 edges. 1, 2, 3, 4, 5, as can be seen. So F has 5 and G has 2. This should be the answer for us. 4, 4, 3, 3, 3, 5, 2. And as correctly pointed out by you guys in chat also, that this corresponds to option C. And option C is right. And now let's move on to the second question then. So in second question, we are asked to identify, we are given a graph. Maybe I should first take this whole question to the next page. Yeah. So what are the cut edge and the cut vertices respectively in the following graph? So this is a more than one choice correct, I would say. So this is not cut edge and not cut vertex, but cut edges and cut vertices. We need to identify all such edges and vertices. So first of all, just to revise you guys the definition for a cut edge and a cut vertex. So cut vertex or a cut edge is just a vertex or an edge whose deletion disconnects the graph or just increases the number of connected components of the graph. As can be seen here, the number of connected components in this graph is just one, since all of this is a connected component. So if this is disconnected on deletion of an edge or a vertex, then we'll call that edge or a vertex as a cut edge or a cut vertex. So just writing down the definitions, which has already been discussed in the lectures also. An edge whose removal or deletion, let's say, disconnects a component. Disconnects a connected. So initially, if it was a connected component, and if gets disconnected on a deletion of an edge, then that edge is called a cut edge. Similar definition can be a cut vertex. A cut vertex is a vertex whose deletion or removal disconnects a connected component. So fair enough. So let's just write down the vertices. Let's identify the cut vertices in this graph. So for finding out the cut vertices, we'll have to look at each vertex one by one and identify whether the given vertex is a cut vertex or not. And we can do this like orally also. We can just see that when we look at the vertex A, okay, so you guys have already answered this in chat also. So Ojas had said that E and B are cut vertices and BE is a cut edge. And same answer has also been given by Kansha. So I'll just go over it once by myself. As can be seen here, if we remove the vertex A, the vertex A is still not a cut vertex because after removing this A, we still have a connected component, not a cut vertex as component is still connected after deletion of A, right? Similarly, when we go to the vertex B, when we see the vertex B, on deletion of vertex B, actually, it can be seen that AGCD is a separate component now because it does not have any edge with this EFH component. So EFH becomes one component, this AGCD becomes the second component. So vertex B is a cut vertex. A cut vertex as it creates, as its deletion creates to here, as its deletion creates two components. That is, once again, we are just revising what has been discussed in the lectures, all of this. And the two components here are AGCD and EFH. Right? Now looking at this vertex C, on deletion of C, again, you can see that it will still be a connected component. And on deletion of this D also, we still have a connected component. On deletion of E though, we'll have two components now. FH will be a component and ABDCG will be a component on deletion of E, as can be seen. Like If we delete this, then this EF does not have any edge in common with this component. So we have two components. So E is also a cut vertex. And I'll just copy this. And what are the components created here? The component A, G, C, D, B, and FH. Right? And you can see that this after E, this on deletion of this F, we still have a connected graph. So F is not a cut vertex. Similarly, G is not a cut vertex and H is not a cut vertex. So remaining vertices not cut vertices. So we only have two cut vertices, B and E. We have to just list down. So cut vertices are B, comma, E. Right? And let's come to the cut edges now. And again, repeating this exercise for edges, we look at all of the edges individually. I'll just go over it a bit faster. You can see that on deletion of this A comma G edge, we still have a connected component. On deletion of the G comma C edge, we still have a fully connected component. Like this is still a single component. Similarly, on deletion of BD edge, we still have a connected component. We still have only one connected component. On deletion of AB edge, again, we still have a connected component. But on deletion of this BE edge, note that these components separate out. So one component becomes EF edge, which has no edge in common with the component ABDC. So one of the edges is B comma E, and this is a cut edge. As it's, maybe I should just copy this. Cut edge as its deletion create two components. And what are the two components? The components are A, G, C, D, B, and E, F, H. Okay. So after this BE edge, again, this EH edge, this FH edge, and EFH, all of these are not cut edges because the component still remains connected. So yeah, so we have the cut edges here as B. B comma B. Right? Okay, so now maybe yeah, should I? Okay, so maybe let's just ask this question. This is an interesting question now. So another question. So this is related to cut edges and cut vertices. So suppose a graph contains at least one cut edge. Here you can see that cut vertices are B and E. And note that cut edge also corresponds to the edge B comma E only. So the endpoints of this edge are cut vertices also. So is there any relation amongst like cut vertices and cut edges? Like, can we say like, so is this statement true? Are the following, okay, maybe I should not bold this. Are the following statements true / false? And what are the statements? If a graph contains a cut edge, then also contains a cut vertex. And the second statement is the opposite of this. If a graph contains a cut vertex, then it also contains a cut edge. Okay. So out of these two statements, do you think if any of this is true or both of these are false or both of these are true? Okay. So Ojas is saying that first is true. So Ojas is saying that if a graph contains a cut edge, then it also contains a cut vertex. What do you think about this, Akansha? Ah, just think about it for a minute. And Ojas, what about the second statement? Is second false or true? Okay. So Ojas is saying second is false and first is true. And Akansha is also typing her answer. Okay, Akansha is also saying one is true. Okay, so okay, Akansha is typing something. Oh, and Akansha is saying second is false. As example, star graph has cut vertex. Okay. Akansha, I think I'll come back to your statement. So Akansha is saying that second is false because an example is a star graph has a cut vertex but not cut edge. Okay. I'll come to your statements. I'll come to your claims. So let's see one by one. So, so what should be the answer to this? Um, actually, 1 and 2 both are false. First of all, let's come to this answer. And why is this the case? Let's just look at 1. What happens in this? So it says if a graph contains a cut edge, then it also contains a cut vertex. And I'll just give an example where this does not happen. So note that if you want to show something is true, then you need to prove it. Whereas if you need to show something is false, then you just need to give an example where this does not hold. An example is consider a graph with vertices A and B. So there are only two vertices A and B. Maybe I should just write it like this. And edges, and there is only one edge in the graph, A comma B. So there are two vertices A and B, whereas there is only one edge, A comma B. So in this kind of graph, what do you think happens? What do you guys think happens? Is there a cut edge in this graph? If there are only two vertices and there is an edge between them, is there a cut edge? And is there a cut vertex? Okay. Ojas is saying that both. And Akansha is saying only cut edge. So, Ojas, why do you think there is a so in this graph actually what I'll be claiming is uh, A comma B is a cut edge but no cut vertex. And why is it the case? Because initially we see that this graph G, okay, I'll just call this graph G. So G is a graph which is connected, right? Uh, G is a connected graph. And now a cut vertex is defined as a vertex whose deletion disconnects the graph. But after deleting, let's say one of the vertices, let's say we delete the vertex A, or let's say we delete the vertex B, there is still one vertex present. And if there is only one vertex present in the graph, what do we call it? Do we still call it a connected graph? Yes, Akansha, exactly. So after deletion of any of the vertex A or B, there is still one connected component. Because if you delete the vertex A, then still B is a connected component in itself. Obviously, it does not have any outgoing edges or anything, but a singleton vertex is also a connected component, right? So that's why there is no cut vertex, but there is a cut edge because there because like on deletion of A comma B, we get two connected components, which are A and B. So is this clear, Ojas? What I'm trying to imply here? Okay, it's clear. That's nice. So that's why, although I get why did you guys answer this true? Because on a high level, when you're deleting a vertex, you are deleting many edges, right? So if there was a cut edge, then that should have been deleted on deleting a vertex, right? So that's why I understood that you guys thought that there might be a, if there's a cut edge, then there might be a cut vertex. And now let's come to the second. Second is also false. So again, we'll give an counter example. So before giving a counter example, I would like to come to the example given by Kansha. So Kansha, you claim that in a star graph, so uh, if Ojas, you don't know star graph, so a star graph is a graph in which one vertex is connected to, so maybe just consider a tree of depth 1. That is what we call a star graph. That there is a root and root is connected to many vertices, but none of the vertices is connected to each other. So in that star graph, there is a cut vertex. The root R is a cut vertex. I agree, Akansha. But you are saying that a star graph does not contain any cut edge. Is that true? Does a star graph not contain any cut edge? Akansha, what do you think? Because like what I am thinking is okay, okay. So I think you get that it contains. So actually, like let's say the vertices are v1, v2 till vn, and there is a root r. So there is a edge from r to v1, r to v2, r to v3 till r to vn. Then if we even if we delete the edge r comma v1, we will have two components. So star graph contains both a cut vertex as well as a cut edge. So that example does not work for us. So should I, maybe I should give this as a do-it-yourself exercise. It's not too difficult, guys. Like you can come up with an example. Just trust me that this is true actually. If a graph contains a cut vertex, then it also contains a cut edge. This statement is actually false. Like, this answer is correct that this is false. And just think about it like when can this happen that a cut vertex is present, but a cut edge is not present. So yeah, maybe I don't want to give the answer to this. It's like it's not too difficult to think, but interest. So Ojas, is the so Ojas, is that clear to you? Like the what is a star graph and why it has both cut edges and cut vertices? Okay, it's clear to you. Nice. So do think about it yourself. It's always good to find counterexamples to claims. So yeah, let's move on to the third question then. Third question. says that the number of components in Kn and Cn respectively are. So what, first of all, just to be clear with the notations, it's not, first let us define what does Kn actually mean. Like this has been discussed in the lectures, but I'll still be. So what do we mean by Kn? Kn is nothing but a complete graph with n vertices. And what is a complete graph? A complete graph is just a graph which has a pair, like which has an edge between all pairs of vertices. So a complete graph on n vertices. And just so you know, so since it is a, since all pairs of vertices have an edge between them, so obviously this is a connected graph, right? So this is a connected graph. And since it's a connected graph, the number of components will just be one. We need to find out the number of components in Kn as well as Cn. So in Kn, we get one component, and Cn is what we call a cycle. So Cn is nothing but a cycle or n vertices. So I hope everyone understands what a cycle is. And what do you guys think? Like the number of connected components in Cn? Okay, so Akansha has already answered in chat that the correct answer is option D. So good job, Akansha, your answer is correct. So a cycle on n vertices is also a connected graph, right? Because you can go from every pair of vertex to the other. So it's a connected graph, and so it also just contains one component. And that's why the correct answer is option D. D is correct. Okay. Now let's come to the fourth question. So fourth question is a bit of a, not a challenging question, but not as simple as the previous ones. For this, I'm hoping you guys have gone through the lectures and you know what Havel-Hakimi theorem is. So which of the first, so the question asks which of the following is a graphic sequence? And what is a graphic sequence? A graphic sequence is a sequence uh, is a sequence of numbers such that if, and we need to answer whether there exists a graph such that the degrees of the vertices of that graph are equal to like this sequence of numbers. So maybe I should just and write this also. So graphic sequence, a sequence of numbers such that there exists a simple graph. So note the emphasis on simple, a simple graph such that the degrees of that graph or degrees of vertices of that graph correspond to this sequence of numbers. So this is what we call a graphic sequence. And how do we identify whether a sequence is a graphic sequence or not? This has been discussed in the lectures that use Havel-Hakimi theorem to find whether a sequence is graphic or not. So maybe we can work through this problem together. First of all, just for revision, I'll just discuss orally what is Havel-Hakimi theorem. In Havel-Hakimi theorem, what we do is if we are given a sequence of degrees, the first thing which we do is sort that sequence in decreasing order. So the first thing which we'll be doing is given a sequence of degrees, we'll sort that in decreasing order. Then we take the first number, basically the largest degree, and we say that we reduce this sequence to another sequence by reducing one from, like, let's say suppose this was the degree sequence given to us. Here 5 is the greatest number. Then what we'll be doing is we select this number 5 Then from the next 5 numbers, we deduct 1 each and make this a 0. And then we'll only have remaining 4 numbers which are non-zero. And note that we'll again sort these. So one thing which everyone struggles with in Howell-Hakimi theorem is you have to sort at every step. What a lot of people do is they sort according to degrees initially and then they forget of sorting at other steps. And this leads to incorrect answers. So please just remember to always sort the sequences in like decreasing order or non-increasing order of degrees at every step. So maybe we can work through the examples. We can work through the question, the different options. So, and what we do in Howell-Hakimi theorem is like, we continue this procedure of like, initially we are given these 6 vertices, then we'll be left with 5 vertices, and then we'll be left with 4. And as soon as we arrive at some vertex like whose degree should be -1, then we say that it is not possible. So I just described the high level idea. Okay, you guys have already arrived at the answer also, and you're saying that only option A is correct. Okay, maybe we'll just take it slow and do it step by step. But yeah, I believe your answer is correct. So still, let's just do it step by step for everyone. So we are given this sequence 5, 3, 2, 2, 1, right? And now when we use the Howell-Hakimi theorem, we for the next, so the largest number here is 5. So what we do is we take the next 5 numbers, which are all these numbers, and reduce 1 from all of them. And we then ignore this 5. So what is left is this 3 becomes 2, this 3 becomes 2, this 2 becomes 1, this 2 becomes 1, this 1 becomes 0. Maybe I'll just copy these and reduce 1 from each of them. So 2, 2, 1, 1, 0. And now we'll again be sorting these in non-increasing order, which has already happened here. So we don't need to do anything. Now we select the largest number, which is 2. And now from the next 2 numbers, I'll reduce 1 each. So I'll just copy these. So these were the degrees initially. And now I'll have to reduce from this 2 and 1 each. So this 2 becomes a 1, this 1 becomes a 0. And note that this keeping it the sequence like this is not correct because I need to sort at this step again. Because all the time I need a non-decreasing order. So after sorting, like this will just become a 1, 1, 0, 0. And this 1, 1, 0, 0 becomes I take the largest number as 1. Then from the next one, I just reduce the value of 1. So this just becomes something like a 0, 0, 0. And if we arrive at something like a 0, 0, 0, Howell-Hakimi theorem says that the sequence is actually graphic. So this sequence is graphic. Hence, the sequence is graphic. Yeah. Now we go to option B. So we'll have to run it for all the options because this might be multiple correct. Now we run the same Howell-Hakimi theorem for all of these. So the initial sequence given to us is 2, 1, 1, 1, 1, 1. And now we select the largest number, which is 2 here, and reduce from the next 2 entries a value of 1. So these were the largest numbers. I reduce a value of 1 from this. I reduce it from this. And note that now these are 2 zeros and these are 3 ones. I need to sort it. So this becomes a 1. This becomes a 0. This is the sorted part. And now I take the largest number, which is this one, and reduce it from the next one, a value of 1. So this becomes more like a 0, 1, 0, 0. So this one will become a 0. So it becomes 0, 1, 0, 0, which on sorting actually becomes 1, 0, 0, 0. And note that after going to this, we'll take the largest value, which is a value of 1. And so from this, we'll be reducing from the largest number a value of 1. So from the 0, we'll be reducing a value of 1, which will come out to be -1 now. And note that since -1 is not a possible degree, so this is non-graphic. Or non-graphic or not graphic, it just means the same. Now coming to option C. Option C has the degree sequence as this 6, 5, 4, 3, 2, 1, 0. So note that, guys, I'm just discussing this in detail because you need to be familiar with the how to implement Howell alchemy. Because a lot of times people do a lot of silly mistakes, like they don't sort at every step or something like this. So in this, we know the largest value is 6. So from the next 6 numbers, we need to reduce a value of 1. But note that there are only 5 numbers present here. There are no 6 numbers present. So we can't reduce a value of 6 because there is no 6 number present. So directly we can say that this sequence is not graphic. This sequence is non-graphic as after removing the 6, we need to reduce degrees of 6 vertices by 1. But we are actually left with only 5 vertices. So this is not a graphic sequence. I hope this is clear to everyone that from this 6 we need, because this 6 we need to reduce the degrees of 6 vertices. But we don't have 6 vertices, we just have 5 vertices. So this is not graphic. Similarly, coming to option D, what we have is this 5, 5, 2, 2, 1, 1. And now what we do is we select the largest number 5. And so we reduce all of these, for these 5 numbers, we reduce the degrees. So this becomes something like, so this 5 becomes a 4, this 2 becomes a 1. And now we have, note that this is not a sorted order. So we need to sort it. So it will be like this. And now we have the largest number as 4. So from the next 4 numbers, we reduce a value of 1 each. So this becomes something like, so this 2 becomes a 1, this 1 becomes a 0, this 1 becomes a 0, this 1 becomes a 0. And now note that this is also sorted. So the largest number here is 1. And now we need to reduce from the next number a value of 1. And as you can see already, that will be coming to a negative number. So this 0 will become a -1. And since we have arrived at a negative degree, hence this is non-graphic. Okay. So okay, I think I done a mistake here? Okay, so yeah, okay, so this is 5 to, I did not reduce all of these values. So I made this 5 a 4, but I may skip some steps. Sorry for that, guys. Maybe I should have been a bit more clear. Yeah. So this becomes something like 5 to 2, 1, 1, and we need to reduce 1 from all of these. So this becomes 0, this one becomes 0. This is what we needed to do, right? And from this 4, we need to reduce the next 4 values by 1. So this would have become a contradiction at this step itself. So it would be 0, 0, -1, -1. And we would have directly said that this is not graphic. So I hope it is clear to everyone. I did a bit of a mistake initially, but I think it's correct now. We still arrive at the same answer. So option B, C, D are non-graphic, only option A is graphic. So option A is correct. Right? Now let's move on to the fifth question then. So just one thing again, remind you guys, like always remember to sort these numbers at every step in non-increasing order. Like you don't just need to sort initially, but you need to sort at every step. Yeah, just getting this message across because this is a very common silly mistake in like quizzes or exams. Okay, so the fifth question asks us, which of the following is not a path from A to H? So we are given a graph and we are given two vertices A and H, and we are given a bunch of like sequence of numbers, and we need to answer which of the following is not a path. So first of all, I hope everyone is clear with the definition of a path. What is a path? A path is just a sequence of vertices which are connected by edges such that no vertices or edges get repeated. So it is a very important property of paths that you should not be repeating any vertex or an edge. If it gets repeated, then that's what you call a walk. If you guys have gone through the lectures, then these definitions have been discussed in the lectures. So like a walk is something where uh, you can repeat edges or vertices. A trail is something where you cannot repeat edges, but you can repeat vertices. A path is something where you cannot repeat edges as well as vertices. So yeah. So let's come here. This is also multiple choice. So let's do this option by option. Maybe I should just zoom out a little. So yeah, figure and options are. So option A says A, B, E, F, G, H. Is this a path from A to H? So A, B, E. So we need to see at every step whether we are connected by edges, and we also need to ensure whether we are not repeating any vertex or an edge. So the path A, B, E, F, G, H. It's claiming like after F, we are going to G. But note that FG is not connected by an edge. So this is not a valid path. So not a valid path has no edge between F and G. Similarly, coming to option B, what we have is A, B, C, H. So this might seem a bit boring, guys, like going through all these options, but I just want to make ensure that everyone is clear on what exactly is a path and what exactly is not a path. So that's why we have a bunch of options. So let's see this A, B, C, H. So A to B, B to C, and C to H. So note that here it can be seen that this is a path. A to B, B to C, and C to H is a path because there are no repeating edges or vertices, and all of these are connected by edges. So this is a valid path. Now let's come to option C. Option C says A, F, E, B, C, H. So A to F, F to E, E to B, B to C, and then C to H. So again, we have not repeated any edge or a vertex, and all of these are connected, and all of these vertices have an edge between them. So this is also a valid path. So option C is also valid. Moving on to option D, we have A to F, then F to C, then C to B, then B to E, then E to D, D to C again, and then C to H. So note that we have repeated the vertex C twice in this path. But as I mentioned already, in a path, you cannot repeat the vertices. So this is not a valid path. So not a valid path as C is a repeating vertex. Right? Let's move on to option E then. Option E says A to F, F to E. Okay, option E says A to F, F to E, E to D, D to C, and C to H. So this will again, we don't have any repeating edges vertices. So this is actually a valid path. Okay. And coming to option F. Option F is A to H. So A to H is obviously not a valid path because there is no edge between A and H. So just copying this. And no edge between A and H. Okay, similarly, this is getting a bit boring. Maybe we should do it a bit fast. So after this, maybe we can do option F. Option G. Option G just says A, F, E, H. So option G is A to F, F to E, and E to H. So note that this is the valid path again because nothing is stopping us. Yeah. So option G is a valid path. Similarly, option H is A, B, C, D, E, H. So A to B, B to C, C to D, D to E, and E to H. So again, we don't have any repeating vertices or edges, so this is also a valid path. So we had to answer which of the following is not a valid path, and we see that only option A, option D, and option F. So A, D, F are not valid, other paths are valid. Hence, options A, comma D, comma F, correct. I hope this is clear to everyone. So Ojas wrote that D comma F is the answer. But note that Ojas, A is also not a valid path because between F and D there is no edge. So these kinds of questions, although they are very simple in essence, but these are more prone to like you are more prone to making silly mistakes in these kinds of questions or just skipping something like you skip this FGH. So it's better to like try to go through these kinds of questions also. So yeah. Now let's move on to the sixth question then. So sixth question is just a very straightforward true false question. So sixth question says that if an edge is removed from a cycle in a graph, then the graph becomes disconnected. Is this statement true or false? Okay. So Ojas claims that this statement is false. Okay, Ojas claims that this statement is true. What do you think about this, Akansha? We are given a cycle in a graph, and if we remove an edge from a cycle, then the graph becomes disconnected. Okay, so Akansha says that the answer to this should be false. So actually, a good job, Akansha. The answer to this is actually false. So, so if an edge is actually removed from a cycle, then the graph will still remain connected. And the reason for this is just maybe just let me give an example of some of the previous graphs. So let's just assume this was the graph given to us. I'm just giving an example. I know like for proving something to like for showing something, you need to prove it, but I'm just giving an example. But you can see that this kind of thing will hold in every graph. So suppose we are given a graph and we have these sorts of cycles like A, B, D, C, G, and E, H, F. So we are given some cycles. And suppose I delete some edge from the cycle. Note that this graph is firstly connected. If I delete this edge AG from the cycle, note that this graph still remains connected. And the high level reason is that a connected graph is a graph in which there is a path from each pair of vertices to each other, right? So for any two vertices in the graph, if there is a path between the two vertices, then that graph is connected. So suppose I delete this AG edge. Suppose this was the cycle A, B, D, C, G. And in this cycle, we know that every pair of vertices has a path between them. But as soon as I delete this AG edge, I still have this alternate path like AB, BD, DC, and CG. I still have this path available, and due to this, I will still have a path between every pair of vertices. So the high level idea is even if you delete an edge from a cycle, there is always an alternate path existing from between any two pair of vertices, which does not use this edge AG. So like, suppose initially I thought that, oh, maybe the path present between A to G is this path, which uses the edge AG. And now if I delete this edge, this path will not be available now. But since it is a cycle, there always will be an alternate path available to us from A to G. So that's why between every pair of vertices, even if we remove an edge from a cycle, the high level idea is it will still remain connected. Does this make sense, Ojas? Or should I try to repeat? I can also try to repeat the argument in a more clear manner. Okay, it's clear to you. Nice. So actually, yeah. So this statement is false, and yeah, if an edge is removed from a cycle, there in a connected graph, the graph still remains connected because like, why does the graph still remain connected? And this is because there is always alternate path present between vertices of the cycle. So because of the presence of an alternate path between vertices of the cycle, the graph still remains connected. Okay. Now let's move on to the seventh question then. Again, seventh question asks is more based on the definitions of like what's a cycle, what's a trail, what is a circuit, and so on. So again, I will be doing this question just so that we are like updated with the definitions, because these kinds of questions can also be asked in the exams. So yeah, we need to be clear with the definitions. Let's do it option by option. So options A says in this given graph, DEF GCD is a cycle. We need to identify whether this is a cycle or is it not a cycle. So note that let's just see this. So DEF GCD. So what do you guys think? Is this a cycle? So note that in a again, like we discussed in a path, a cycle is something which starts at one vertex and ends at the same vertex. But between these two vertices, like it starts at D and ends at D, between these two vertices, there should be no repeating vertex or an edge. This is what a cycle is. And this is, so yeah, Ojas, you're correct that this is indeed a cycle. Because there is, so it starts at the vertex G, ends at the vertex G, and the path in the middle, the D, E, F, G, C, D, does not contain like repeating edges or repeating vertices. The only repeating vertex is the vertex G itself. So this is what we call a cycle. So yes, it is a cycle. Is a cycle. Now coming to option B. So option B asks us whether this is a trail or not. So note that in a definition of a trail, what we need is like every consecutive pair of vertices should be connected by an edge. And like we can have repeating edges. Okay, sorry. We can have repeating vertices, but we don't want to have repeating edges. So in a trail, we don't have repeating edges. We can have a repeating set of vertices though. So let's just see here. So this trail starts from edge, edge to B, B to D, and D to C, C to G, G to F, F to D, and D to A. So it traverses something like this: HBD, CG, FDA. This is the sort of way we are taking. Here, and this. So what do you guys think? Is this a trail or not? Yes, so Ojas is saying that it is a trail. So good job, Ojas. As you can see, like here the vertex D is repeating while we are doing this. But in a trail, vertices can repeat. The only thing is edges should not be repeated. And every consecutive pair of vertices should be connected by an edge. So all of these are connected by an edge and no edge is repeating. So it is a trail. Yeah. Similarly, coming to option C. So whether option C says that ABDA is not a cycle. So let's go through this. AB, BD, and DA. So this is a simply like it can be seen that this is actually a cycle. Like it starts at A, it ends at A, and like no repeating vertices or edges. So is a cycle. So is a cycle actually. So option C will actually be incorrect. So option D says ABDCDF is a tree. Let's see this. So AB, BD, DC, CD, DF. So A, B, B, D, D, C, C, D, and DF. So again, here you can see that every pair of consecutive vertices is connected by an edge. But like in a trail, we don't want repeating edges. But you can see that while going from A to B, B to D, then we first went from D to C, we took this edge, and then we went back from C to D. So we again took this edge. So that's why this is not a trail. Like this CD edge is getting repeated. So note that even though it is this edge once was taken in this direction from D to C and next time in C to D direction, but since an undirected graph, we don't talk about directions and we'll still say that this edge has been taken twice. So that's why this is not a trail. Not a trail as edge CD taken twice. Similarly, let's move on to option E. Option E says A, B, B, D, D, C, C, G, G, F, D, A is a circuit. So again, definition of a circuit is basically it should start and it should end at the same vertex, and all the consecutive pair of vertices should be connected by an edge. In a circuit, like we can have connected, like we can have repeated edges as well as repeated vertices, as far as I know. So we just want to ensure that we start and end at the same vertex and every pair of vertices is connected to each other. So A to B, B to D, D to C, C to G, G to F, F to D, then D to A. So we start at A, we end at A. Like this is the way we took A, B, D, D, G, G, F, D, A. So here it can be seen we started at the same vertex and like, yeah, every pair of vertices is connected. Every pair of consecutive vertices is connected with an edge. So yeah, so this is actually a circuit. So this is a circuit. Okay, so option E is correct. Option D is not correct. C is not correct because it is actually a cycle and C claims that it is not a cycle. And A and B are correct. So options A, B, E are correct. Right. I hope this is clear to everyone. If not, you can ask me in chat. Okay, Ojas is typing something in the chat. Okay, so it is clear to Ojas. Nice. Okay, then. So maybe after this, we can move on to the eighth question. So eighth question says that which of the following statements are true? So we are given a bunch of statements and we want to find out which of the following are true. So the first question, the first part says that if there is a walk from P to Q, then there must be a path from P to Q. So, okay, let's just see. Let's just see this statement by statement. So, what do you guys think? Like, first of all, what is a walk? So, a walk is again a sequence of vertices such that each consecutive pair of vertices has an edge between them. Okay, maybe I should just let you guys remind you these definition because maybe I should just write it down in the starting itself. So what's a walk? So walk is a sequence of vertices such that every consecutive pair of vertices has an edge between them. All of these definitions have been covered in the lectures also, but just for revision of everyone, I'm just defining these again, like so that you don't have to go look again at the lectures. Similarly, a circuit. What is a circuit? So circuit is, so note that in a walk, uh, vertices as well as edges could repeat. It's just that every consecutive pair of vertices should have an edge between them. And what's a circuit? Circuit is a walk which starts and ends at the same vertex. Similarly, another thing which we have is a trail. A trail is a walk in which no edge is used twice. So this is how we define trail and this is how we check trail. Similarly, we also have what we call a path. A path is something, so a path is nothing but a walk in which no edge and no vertex is used twice. So note that if an edge is used twice, then anyways a vertex will be used twice. So we can relax this condition. Because like if we are using an edge twice, then we'll be using the endpoints of that edge twice. So that means that vertex will be used twice. So this is a stronger condition, and we can just directly say that no vertex is used twice. Or maybe like we should say occurs twice. A walk in which no edge occurs twice, a walk with charts. So yeah. And similarly, another definition which we covered was what is a cycle. So a cycle is a walk. Or maybe let's say, okay, so maybe we can define cycle in terms of circuit or walk. Maybe let's just define it in terms of a walk. A walk which starts and ends at the same vertex and no edge slash vertex appears twice. No edge and no vertex appears twice, except the starting vertex, which appears only at the start and the end. So this the definition of cycle becomes a bit technical. So first we defined a circuit which starts and ends at the same vertex, a trail in which no edges occur, a walk is a path is something in which no vertex occurs twice, and now um, a cycle is something which is a walk which starts and ends at the same vertex. So this part is same as trail, a circuit, sorry. So this part is same as a circuit. So basically what we can say is a cycle is a circuit such that no vertex and no edge appears twice, except the starting vertex, which appears only at the start and the end. So note that no vertex should appear twice, So again, we can relax this criteria that no edge appears twice because no vertex is a stronger condition, as we have already talked about in train and path. So yeah. So a walk is a walk which starts and ends at the same vertex, and no vertex appears twice except the starting vertex. And that starting vertex should only appear at the start and the end, and it should not appear in the middle. This is also important. The starting vertex also only appears twice, and but it only appears at start and the end, and not at anywhere in the middle. I hope these kinds of definitions are clear to everyone. Like, these are something which we have already discussed in the questions also, but just so that everyone uh, maybe just remembers them, I just wrote it down here also, just for it. So yeah. Okay. So I hope this is clear. Then maybe we can uh, move to this question. So the eighth question says that if there is a walk from P to Q, then there must be a path from P. So a walk was just a sequence of vertices which are connected by edges. And now a path is something where no vertex should repeat twice. So what do you think? Is statement one correct or incorrect? So Ojas has written one is false, whereas Akansha has written true. So actually, again, Akansha, good job, you're correct. So Ojas, actually, this statement is true that if there is a walk from P to Q, then there must be a path from P to Q. And again, a high level idea is suppose there exists a walk from P to Q, then there can exist repeating vertices, right? Like a path is something where no vertex gets repeated. A path is a walk where no vertex gets repeated. But in a walk, like a vertex can get repeated, right? So suppose we have a walk from P to Q in which a vertex gets repeated. Let's say that vertex is V. So a vertex V exists which gets repeated in the walk. Then what we can do is so V must be repeated multiple times, right? There must be the first time which V occurs, and there must be a last time which V occurs. Like what I'm trying to claim is suppose the walk goes like this. So it goes from P to, let's say, some vertex. Like maybe like it goes through somewhere, and then V occurs for the first time. Like from P we go to some vertices, and after some vertices, this is the first occurrence of V in the walk. And then again there are some occurrences, and then this is the last occurrence of V in the walk. Note that as V occurs at least twice, it can occur multiple times, but we know that V occurs at least twice. So this part must exist in the walk. And after this, we know in this part, the part which I'm writing now, V does not occur. In this highlighted part, V does not occur because we already said that this was the place where V occurred for the last time. So this part, we know that V does not occur in this path. Similarly, we know that V does not occur in this part because this was the first time V occurred. So what we can actually do is maybe just call this a vertex U. So if this is the walk which is given to us, then we can convert it into a path actually. And how we can do is if V was the repeating vertex, what we do is we just take this part. Till this part, we know that V only occurs once because from P to U, we knew that V did not occur. So from P to V only occurs once. So we take the part from P to V. And then afterwards, we just skip all of this part. If we skip all of this part, all the occurrences of V here are gone. And we just directly assume that we can start from here again. Because this V is the same as this V. So we can start from here again. So we can just start from here and we can append this part. So this, if we call W, then now we have reduced the original walk where there were multiple occurrences of V to a path where there is just one occurrence of V. So this is what we call sometimes short circuiting, that these two nodes are anyways V, so we can merge them into one node. So we can consider all of this as a single node V, and now P to U, then U to V, then V to W, and W to Q will be a walk in which V is only contained once. And we can do this always to remove all the vertices which are occurring more than once. So does this make sense, or just or should I try to explain it a bit more using diagram? Uh, so is this clear, or should I explain it more? Okay, it's clear to you, just nice. So this is just an illustration, maybe I'll just read it. Statement 1 is true. And the high level idea is we can always short circuit a repeating vertex. And statement 2 says the number of edges in a tree is equal to one less than the number of vertices. So yeah, like this is something which should have been discussed in the lectures also, and not too hard to see that yeah, this is true. And statement. So if the number of vertices is, let's say, n, then the number of edges in a tree is just n minus 1. And statement 3 says every graph has an odd number of odd degree vertices. So what do you guys think about this? So does every graph have an odd number of odd degree vertices? Okay, so was it saying false? And Kansha is also saying false. So good job, guys. So this is false. And this is due to the handshaking lemma. Handshaking lemma, which has also been discussed in the lectures. And what does handshaking lemma say? Handshaking lemma says that there are an even number of odd degree vertices in a graph. In every graph, there are even number of odd degree vertices. This is what handshaking lemma says. And the proof of that is using the fact that sum of degrees of a graph is even. So even if we take out the even degree vertices, then the sum of odd degree vertices should be even. And that's how we get that every graph has an even number of odd degree vertices. So yeah. So only statements 1 and 2 are correct. Right? Okay. So we have covered the main problem, like which are sort of uh, more easier problems. We have covered them till now. And now, like usual, we'll have one more problem which is a bit more involved and uses some more techniques, which like basically a problem which requires a bit of more thinking from your side and not directly implementing stuff from the lectures. So yeah. So this ninth problem says that suppose every vertex in a simple graph has at least degree of k. So we are given a simple graph, first of all, and the degree of every vertex is at least k. So it can be more than k, but it cannot be less than k. Now we have to prove that the graph has a path of length at least k. So we have to show that this graph will always have a path of length at least k. So this is a bit of a tricky question. Like it's not too hard, but yeah, this is more involved than the previous question which we have discussed. And I would like to you guys to think about it for like let's say 5-10 minutes. So it's 7:24 now. Like I'll mute myself till 7:30 till 7:30, and you guys can maybe think about it. And just if any idea comes to your mind, like how can you prove this or what can be done, or then you can just simply type out the high level idea in chat. Even if it is incorrect, just I would prefer that you guys try to still attempt proving this kind of thing. Even if your proof is incorrect, but you still need to, it would be good if you try to start thinking on your own about stuff. So yeah, I'll be muting myself and we should try this for 5 minutes. Even if you don't get the complete idea, just try to write down whatever you're thinking, even that works. Try to attempt even one or two ideas, even if you don't have the complete solution. Okay, so Ojas is typing something in the chat. Okay. Oh, okay. I think Ojas, I maybe wrote the question I wrote was a bit unclear. So so Ojas is saying that this given statement is actually false because, as an example, if there are four vertices, each of degree 2, then there is also a path of length 1. So the question is not asking that uh, the graph, like every path will be of length 1. The question, every path will be of length at least k. This is not what the problem is asking, because this is always trivial, because if we anyways take an edge u comma v of a graph, then u comma v will be always be a path of length 1. So the problem is saying that the graph has a path of length k. Like every path does not have length k. There exists at least one path which has length k. So maybe I should write it better. Prove that there exists a path in the graph which has length at least k. So this is what the problem is asking. Would you like some more time to think about it? 3-4 minutes if the problem is clear now? Or should I discuss the solution? It can be proved by induction. I think using induction might be somewhat difficult here. Like if you do induction on degree, then note that there can be a lot of vertices with degree at least k, right? Suppose we know that, yeah, like by induction, I think this will be a bit tricky, or at least I don't know a straightforward way of using induction. Because if, let's say, every vertex has degree at least k, and now you want to ensure that every vertex has degree at least k plus 1, I don't know exactly how will you be able to do that. Uh, so yeah, I'm not sure if this would be the right way to go induction. But yeah, maybe it can be done, but I don't think it would be straightforward. So yeah. So anyways, I think in that case, I can discuss the solution. So first of all, like I just want to make clear that what do we mean by length of a path? Length of a path. I hope everyone knows it already, but yeah, is just equal to number of edges, right? Number of edges in a path. And now to prove this claim that exists a path in the graph which has length at least k, we'll do it using proof by contradiction. And what does proof by contradiction mean? Proof by contradiction means that we will assume that this thing is not true. So what we have is G is a graph. So there exists a graph G such that degree of every vertex is greater than equal to k, and assume there exists, I should write it like this. Assume there exists a graph G where a degree of every vertex is greater than or equal to k, and no path, or maybe like, and G does not contain any path of length greater than or equal to k. So suppose like we are doing it by contradiction, so we have to write simple graph as well. Yeah. So we are doing it by contradiction. So we assume that what is given to us is not true, that there will exist a graph where degree of every vertex is greater than or equal to k, and the graph does not contain any path of length greater than or equal to k. So if this is true, then this means that all paths in this graph have length less than k, right? So if no path has length greater than or equal to k, this means that all paths of G have length less than k, right? If a path length is not greater than or equal to k, then it would be less than k, or we can write it as less than or equal to k minus 1, because path length is integral. So it would be like, if less than k, then it is also less than or equal to k minus 1. And now what do? We know that all paths have length less than or equal to k minus 1. So from this we can say that the longest path will also have length k minus 1, less than or equal to k minus 1, right? Even the longest path in G will have a length less than or equal to k minus 1, as all paths have length less than or equal to k minus 1. So longest path of G also has length less than or equal to k minus 1, right? And since it is less than or equal to k minus 1, let's assume like this can be proved for all cases, but I'll just assume that. Let's assume, because I'll be showing you guys a graphic illustration so that the proof is more clear. So let's just assume that length of longest path is k minus 2. So it can be k minus 1 also, and the proof still goes through. It can be k minus 3 also. So it works for a general length less than or equal to k minus 1. But I'll be drawing up some vertices and showing you guys how the proof goes. So just for graphic illustration, for now I've assumed that length is k minus 2. But same proof, same proof works for all lengths less than or equal to k minus 1. And for general lengths, maybe you can try yourself. Like I'll be just showing for k minus 2 is a graphic illustration, but this works generally, and you can see for yourself while this works. Yeah. So let's just see the longest path first. So this is this is a graphic illustration which I already drawn. Yeah, the second illustration will come later. But yeah. So let's assume the longest path has length k minus 2. So this is the longest path in the graph G. If there are if there are k minus 2 edges, then there will be k minus 1 vertices in this path, right? So there will be k minus 1 vertices, and it can be seen that these will be k minus 2 edges. So the path is, let's say, the longest path starts from V1. It says V1, V2, V3, V4. And we know that in a path, no repeated vertices or edges are present. So it goes from V1 till Vk minus 1, and there are k minus 2 edges. So let's assume this is the longest path. And now we know that the degree of this vertex, the vertex V1, is greater than equal to k. Because in G, all vertices have degree greater than equal to k, right? Since all vertices of G have degree greater than equal to k, this means degree of V1 is also greater than equal to k. V1 is greater than or equal to K. Right? And note that these vertices, these V2 to Vk minus 1. So we see what all edges can V1 have. So V1 can have an edge to V2, it can have an edge to V3, it can have an edge to V4, it can have an edge to Vk minus 1. But basically what we need to ensure is that degree of V1 is greater than or equal to K. So V1 should have at least K edges connected to it. But note that even if V1 has edges, we know that V1 has an edge to V2. Even if in the worst case, let's say V1 has edges to all of these vertices, V2 to Vk minus 1. Then note that these are just K minus 2 vertices. Right? Because all of this set is K minus 1 size, and there is this vertex V1. So remaining vertices are K minus 2 vertices. So apart from these K minus 2 vertices, V1 should have at least 2 more edges, right? Since degree of V1 is greater than or equal to K, so V1 will have at least 2 more edges outside of this. So let me just write it down. Since V2, V3 till Vk minus 1 are only K minus 2 vertices. Hence, V1, or let's say just one small, V1 will have at least 2 vertices which are neighbors of V1, because V1 needs at least K neighbors, right? And V1 needs K neighbors, but these are maximum K minus 2 vertices. So note that even in all of these also, some of these vertices might not be neighbors, but in the worst case, let's assume all of these are neighbors. Then still V1 will need at least 2 more vertices which are like outside of this path. So 2 vertices which are neighbors of V1 but are not part of this path. And what does this ensure? This implies that there exists a vertex V. So there is a vertex V which is not part of these set of vertices. Vertex V which is a neighbor. So there exist 2 vertices, right? Which I said 2 vertices which are neighbors of V1 but not part of this path. So let's assume one of that vertex is V. So there exists one of a vertex V which is a neighbor of V1 but not part of the path. Okay, which is a neighbor of V1 but is not part of the path. And so what the picture will look like now, let's see. I'll show this diagram to you now. Yeah. So the picture looks like this now, that there is a vertex V which is a neighbor of V1 but is not a part of this path. And now I claim that firstly, what did I assume about this path? Sorry for this guy. So we assume that this path was the longest path in the graph, right? The path starting at V1 and ending at Vk minus 1 was the longest path in the graph. But now actually you can see that I get an even longer path. I see an even longer path, which is the path which starts at V. Like I go from V to V1 and I tread this path then till Vk minus 1. So this V to V1, then V1, V2, V2, V3, V3, V4, V4, V5 till Vk minus 2 to Vk minus 1. So note that initial path was of length k minus 2, and we assume that this was the longest path. But now we have obtained another path. This path is length k minus 1 because one more edge is added. And so like the original path which we assume to be the longest is actually not the longest. And so we obtain actually a contradiction. So maybe I should just write it down that consider the path V to V1, V1 to V2, and so on till vk minus 1. Yeah. Now, this path has length equals to k minus 1 because earlier I had k minus 2 and now one more edge is added. So this has length k minus 1. But this is a contradiction. And why is this a contradiction? Because this, we assume that initial path was the longest path and now we have obtained an even longer path, which is not possible, right? But this is a contradiction as v1, v2 till vk minus 1 was the longest path. And so no path would have been longer than it. So we arrive at contradiction. So we arrive at a contradiction, and what does this contradiction imply? This contradiction implies that, yeah, like what we assumed here was not true, that G does not contain any path of length greater than or equal to K. This is not true. And so, like we can say that hence there will exist a path in G of length K. And this is how we have proved it. Hence, okay, this is a bit like not too hard, but this is uh, a bit longer than usual argument, right? Does this make sense, guys? So what we did was we just tried to prove this using contradiction, and in contradiction we assume that like this given statement is not true, so there exists a graph in which degree of all vertices is greater than or equal to k, but the path has length less than or equal to k minus 1. All the paths have length less than or equal to k minus 1. Then we took the longest path in such a graph, which would also have a length less than or equal to k minus 1. I just took one example to show you guys an illustration, but you could have done this for any length less than or equal to k minus 1. I assume length is k minus 2. So we'll have length k minus 2 when we have these sets of vertices. And now we know that since all set of vertices have degree greater than or equal to k, we just looked at the first vertex of this path and we said that this vertex has at least k neighbors, right? But these are at maximum k minus 2 vertices. So there must be two neighbors of v1 which are not a part of this path. So we consider any such neighbor. So consider this neighbor v. So for this v, we know that v has an edge to v1. And now we obtain that this v, v1, v2, v3, v4 till vk minus 1 is another path. And this path has a length of k minus 1. But we assume that the maximum length was k minus 2 initially, which was of this path. So we actually arrive at a contradiction. And so like this is incorrect and every path, and so there will always exist a path less than greater than or equal to k length. So does this make sense, guys? Or should I try to explain it further? Ojas, Akansha, should I repeat some arguments if they are unclear to you? Okay, it is clear. Nice. So yeah. So this was a bit of a different question from the ones which we have discussed. So I would like you guys to think about it on your own yourself. Like you should try it out. Like when we take instead of k minus 2 any arbitrary length, which is less than or equal to k minus 1. Why will this hold true? It's not too hard to see, but yeah. Okay. Other than that, I guess this was all the questions which I had for this week. So yeah. The first 8 questions were not too difficult, but yeah, ninth was a bit different from the existing questions. So yeah. Okay then guys, I guess if no one has any doubts, then we can close the session and you can leave. So once again, thanks for joining the session, guys. Hope you enjoyed it and hopefully we'll see you guys next week again at the same time, Monday 6 to 8 p.m. So till then, goodbye, guys, and good night.